In this lesson, we're going to be looking at some weapon design considerations. Now, by necessity, this is going to be kind of a short video because there's a lot of stuff that we really can't talk about in an unclassified environment. Now, these three figures you hear that are here up on the screen are the only officially approved DOE figures that can be used in an unclassified environment. The first being a gun assembly style weapon, the second being an implosion assembly style weapon, and the last one being a very basic drawing of a thermonuclear device. Now, when you're talking about this stuff in an unclassified environment, especially if you have a clearance, you cannot go into any specifics about weapon designs, even if you know them. So no talking about any specific material requirements, fission requirements, fusion requirements, just none of that. If you really want to know exactly what you can and cannot say, you can look at DOE's Release of Declassified Documents publication, or RDD. So currently they're at RDD number 8. I don't have a link for it right here. You can Google DOE RDD-8 and it'll come up, and it tells you in no uncertain terms exactly what and what cannot be discussed in an unclassified environment. So if you even remotely think that it may come up, familiarize yourself with the rules, or better yet, just don't say anything at all. Now, when we talked about fission chain reactions, we talked about a couple of different things, and it boils down to there are three things that are really important to us, right? So the number of neutrons we're generating per fission event, the number that we're losing per fission event, and the amount of time that it takes between fission events. Now, two of these things, they're intrinsic to the material and to the process. So one is the number of fission neutrons produced per fission. That is generally a function of the fissile material itself, although it does have some dependence upon incident neutron energy. Generally speaking, the higher the energy of the neutron that comes in, the more likely you are to produce more neutrons than normal, like say the absorption of a thermal neutron. Okay, the second thing that doesn't change is the time between generations. Well, I say it doesn't change, but what I mean is in a non-moderated assembly, like the ones we're talking about for weapons, there's nothing to slow the neutrons down, so the 10 nanosecond time scale is the one what we use. If we were in fact talking about a nuclear power reactor where all of those fission neutrons are really slowed down to thermal energies before they're used, down to now we're up into the millisecond time scale. Okay, that's something completely different. But in our application, that 10 nanoseconds, it's kind of just built into the system. So that leaves us with the number of neutrons that we're losing per fission event. So how do we really lose neutrons out of our assembly that would result in either a slow climb on the fission chain reaction buildup, a steady state condition, or it just doesn't work at all? Well, it has to do with the volume of the material that we're looking at and or the density. Now, the volume, you can basically just take the volume of material and make it big enough so that, generally speaking, most of the neutrons that are born from the fission events inside of it, they're not going to escape. Their path length is not nearly long enough to get them out of the material. So that's one way you could do it. The other way you could do it is you could take material and make it more dense than it is normally so that there are more nuclei per unit volume so that the neutrons have a much higher probability of seeing the nucleus and causing it to undergo fission. So those are the two things we can really change, is the volume size and the volume density. Now, a note on criticality before we get into the design stuff. So there are three regimes for criticality. There's subcritical, critical, and supercritical. Now in the movies, it sounds like a scary thing, right? Oh, the reactor's gone critical. Okay, so it's sort of staying the same. And I'm concerned because... So, Hollywood never gets it right. Now, starting with subcritical, what this means is that you're producing less than one neutron per fission event. Okay, so if you're producing less than one, what's going to happen is your fission chain reaction is just going to peter out, or it's never going to start in the first place because you just don't have enough neutrons. So you're never climbing that exponential hill. Now contrast that with exactly even, or a critical assembly, which is where you're producing exactly one neutron per fission. So every time you get a fission, that creates another fission, and so on and so forth, so that your total population of neutrons and fissions per second never decreases and never increases. It's perfectly level. And then the last regime is the one that we're interested in, which is supercritical, which means you're producing more than one neutron per fission event that can be used, that doesn't, that you're not losing. So subcritical, you don't have a big enough volume, or your volume's not dense enough. Critical, it's like the Goldilocks zone. It's exactly perfect to maintain that fission chain reaction without going up or down. It's not really the Goldilocks zone for our intents and purposes, but that's kind of what you refer to in the nuclear power industry, because for the most part, unless they're ramping up in power output or climbing down in power output, they want it to maintain exactly level, which is the critical regime. And then for us, because we want something to go boom, we need it to be supercritical. So we need that increased growth per generation, which means we need more than one neutron per generation that's going to be used for additional fissions. So let's put it all together. Now, supercritical mass, if you had a supercritical mass just sitting there and you were anywhere near it, things aren't going to go so well for you, because you may not intentionally be introducing neutrons into it to start that fission chain reaction going, but there are other sources of unintentional neutrons, that may be present. The big one is cosmic neutrons. These are really high energy neutrons that are produced via cosmic and solar radiation. They come down through the atmosphere, and they can find your little supercritical mass and start the fission chain reaction going. Now, it's not going to be a bomb, right? Because there's nothing that's going to really hold it together. But what's going to happen is you're going to get an extreme pulse of radiation that comes out at a dose level high enough to kill you. If not immediately, then very, very closely after that. Something I recommend you guys looking up with regards to a supercritical unintentional type chain reaction starting is something called the Demon Core at Los Alamos National Laboratory. So look that up. And so the neutrons weren't entirely unintentional, but the supercritical assembly being supercritical was in fact unintentional. Just look it up and sort of see what happened. So the solution to this is actually what they originally had designed that core, the so-called Demon Core, was that you take your supercritical assembly and you cut it in half or into multiple pieces and you separate them. So by being separated, you now have two subcritical assemblies. It's not possible for them to sustain a fission chain reaction. The other way you could do it is that you could have a subcritical volume and compress it until the density becomes such that it is a supercritical volume. So we can either take pieces and put them together, or we could take something and squeeze it until it becomes supercritical. Now, these are kind of like the knobs that you can play with, the settings, if you will, that can be adjusted to customize your critical mass or your supercritical mass to whatever application you happen to have. And for those of you too young to remember what knobs are, think of them more as sliders. Not sarcastic, not at all. Okay, so gun assembly. In a gun assembly style weapon, this is the official diagram that we'll be referring to, is you take your supercritical assembly of fissile material, chop it in half, assume here it's a sphere so that you end up with two hemispheres, and you separate them. You put them inside of a tube of some sort, and you close the tube on one end, you put one half there, and then on the other end, you take and pack a bunch of explosives behind the second half and set them off, and then you drive them together very quickly. The reason it's called gun assembly style is because basically that's what you're doing. You're using that second half and shooting it like a bullet into the first half. And what you're trying to do is you're trying to assemble these halves very quickly so that your fission reactions don't start until that supercritical mass is already assembled. So you're probably asking, well, how do we make sure that our fission chain reaction occurs right as they come together? And that's a good question. And it basically boils down to, in the very early days, they would use two different materials, one that emitted alpha particles and one that would absorb an alpha particle and then spit out a neutron. Now, the alpha emitters are like plutonium or polonium or americium, and the alpha N reacting material is beryllium. So beryllium, if you get a high enough energy alpha absorbed, it will spit out a neutron. So in effect, what you could do is you could coat one side in your alpha emitter and the other side in beryllium, so that when the two halves came together, the alphas would interact with the beryllium, produce neutrons, and boom, your chain reaction is started. Now you probably say, well, how do I know it's going to start producing neutrons at the exact right time? Well, alpha particles have a very small range in basically anything. Even in air, they only travel, very, very small distances, microns to millimeters, maybe. So even though this one half has got all these alphas being produced, it's not going to start producing neutrons until the halves basically just come together. So that's how the timing on that would work. Now, if you ever hear, there are some shorthand notations for these different initiators within the nuclear industry, and they're called, for plutonium, polonium, and americium, PUBI, POBI, AMBI, and then there's americium lithium, which undergoes a very similar type reaction. So if you ever hear those terms being discussed, it's going to be within regards to a neutron emitter. Now, another consideration with this style assembly weapon is that you have to have something beefy, right? That's going to hold, not only hold both halves, but be able to withstand the force of one being slammed into the other at thousands of feet per second. So it's going to have to do that without letting them squirt out at the end. It's going to have to be able to contain whatever explosion you set off in order to drive the two halves together. And then as a tertiary, it's going to have to contain your fission chain reaction until enough energy is generated so that you get a nuclear yield. Now, this becomes important in the next lesson talking about X-rays because the casing and how the weapon's constructed actually has an impact on what kind of X-rays do we see. So, implosion assembly weapons are a little bit different. Instead of messing with the volume, in the case of two subcritical to put together to make one supercritical volume, we start with a subcritical volume and we squeeze it. And we squeeze it until the density becomes such that it's a supercritical volume. Now, how do we squeeze it? Well, obviously, we use explosives because, of course, we do. Now, there's something that has to be taken into consideration here, as well as with like we talked about with the gun style assembly. It's a little bit different though, and that is, if you want to compress your spherical core, which is what we see in this official diagram, you kind of have to have your explosives all the way around it, and they all have to go off at exactly the same time so that they produce a pressure wave that completely and symmetrically compresses that core into that critical or supercritical assembly. Now, if you're a little bit off with where your explosives are or the timing on your explosives, what's going to happen is you're going to create an area of lower pressure than the rest of the volume. And that lower pressure, the material is going to want to flow from the high pressure region where it's being squeezed into that low pressure region. And what did you just do? You just created a low density area to what should have been a completely high density material. And the material is going to channel neutrons, if you will, out of the lower density area, and they're just going to escape. Now, how bad of an impact it has on your weapon design depends on, well, how bad did you mess up? So you could get sort of a reduced yield if it's not too deformed, or if it's super deformed, you'll get no yield at all because you're going to end up in the subcritical regime because your neutrons aren't going to stick around. They're just going to leave out of that low density area. Now, what about boosting? So when we boost, we're basically taking and creating fusion neutrons somewhere within our nuclear device so that those neutrons can be added to some generation of our population in order to increase our overall yield prior to disassembly. So how are we going to do that? Well, the only way we're going to get the temperatures, if you recall from the fusion discussion, the temperatures necessary for fusion to occur are in the millions and tens of millions of degrees. Well, luckily for us, as it's building up energy and depositing it into our fissile material, our fission core is going to be generating temperatures towards the end in the millions and tens of millions of degrees. So basically all we have to do is take our fusion isotopes, stick them in the middle, and as the fission reaction progresses, we're going to naturally get the temperatures required for fusion to occur, and we'll get those neutrons produced and inserted into one of the later generations of the fission reaction and boost the explosive power of the weapon. Now, when we talk about the isotopes that we'd like to fuse, the best ones, the most energetically favorable, are deuterium and tritium. And not only that, but it produces that high energy 14 MeV neutron. And again, because the number of fission neutrons produced is somewhat related to the incident neutron energy, these high energy fission neutron or fusion neutrons are kind of what we want to increase the output of our weapon. We got a problem though, and the problem's twofold. One, tritium is radioactive. It's got a half-life of about 12 years. So what that means is if you don't immediately use it, that tritium is going to decay over time and not be useful anymore. In fact, it'll decay to the point where you're not really going to have many tritium atoms there to fuse into, and the impact it'll have on your weapon becomes very much diminished. Now, second is that, well, it's hydrogen gas, both deuterium and tritium. And so to get enough atoms or nuclei into the space that we would have available to us, we'd end up, we could put the gas in there, but it's such a low density, we're not going to get a whole lot of reactions because there's not that many nuclei there. So how do we sort of overcome this? Well, let's start looking at the deuterium-deuterium reaction. Okay, so the DD. Now we have two different pathways it can take. One produces helium-3 and a neutron, but the other one produces tritium and a proton. So if we only had deuterium and no tritium, if we heated it up enough and started those fusion reactions going, eventually we would be producing tritium, right? That could then fuse with deuterium that was already there. And so we could get some, not many, but some of those 14 MeV neutrons. Now, a different reaction, one that we really haven't talked about, is the lithium-6 plus neutron reaction, which results in a helium-4 nucleus, but also produces tritium 100% of the time. So what we could do, in theory, is we could take lithium-6 and deuterium and put them together and put them at very high temperatures so that the deuterium starts to fuse together, producing tritium and neutrons. The neutrons will then go interact with the lithium and produce tritium, and then we get the deuterium interacting with the tritium and producing those high energy neutrons. Well, as it turns out, this is actually a thing that's been done, and the combination of the lithium and deuterium is called lithium deuteride. And it's a solid at room temperatures, which means you can pack a whole lot more nuclei into the same space than you could with something like gaseous hydrogen. Now, again, you could take and chill the hydrogen down so that you have liquid hydrogen, so then you would have some very dense material. But the amount of energy required to cool that stuff down to basically not very far from absolute zero is tremendous, and it has to be continuously chilled or it will just expand. And you really don't want expanding gas in the middle of your very precision machined nuclear core, because if it expands for long enough or rapidly enough, it's basically just going to break apart your core, and that's not going to work. So the lithium deuteride has been used, and it has been used to incredible effect in the Castle Bravo test. Now, it's important to note with the Castle Bravo test, if you're not familiar with it, please go look it up. And what we're going to find, or what you will find, is that the other naturally occurring isotope of lithium, which is lithium-7, will also interact. And because of that, unintended consequences occurred. I don't want to spoil it if you don't know what I'm talking about. Just go look it up and see what happened. For those of you who do know what happened with Castle Bravo, see, just a tiny little difference or miscalculation can sometimes have unintended and catastrophic consequences. Finally, the last thing I want to talk about is the fact that theoretically there's no limit to a fusion yield. That is, the limit to fission devices is that exponential curve of energy being deposited over time. Eventually, you get to the point where there's just too much energy and there's no way to hold it together. Fusion's quite a bit different because the fusion can all happen basically at the same time, right? If you create the conditions of the high temperatures and you have all of the different isotopes available that need to be fused, they don't have to wait generation after generation after generation. They can all just literally just fuse within one generation or 2 generations. And so you can create an enormous number of neutrons and an enormous energy yield, practically instantaneous. And so in that sort of vein, we have this no upper limit on what a fusion yield could be. Theoretically, can we do it? No, we can't even build a pure fusion weapon because the engineering challenges are so incredibly daunting that we haven't quite cracked that one yet. But again, no theoretical limit to a fusion device, which kind of comes into play when talking about thermonuclear weapons. But again, very limited as to what we can say in this particular environment. So that's all I have for you for this particular lesson. In the next lesson, we're going to look at X-rays within the context of a weapon. Where do they come from? And what kind of characteristics do they have? And what is the end result of X-ray production? Until then, we'll see you.